Welcome back. We are going to be looking at limits of rational functions at infinity. So let's say I want to find the limit of this rational function as x goes to infinity. Now let's recall from the previous video that when x is big in the positive or in the negative direction, it doesn't matter whether x is negative or positive, as long as x is big in absolute value, the value of a polynomial is approximately given by the leading term. So when x is big, the leading term dominates the remainder of the terms of the polynomial. So when x is big, we can say that the limit of the numerator is okay. So when x is big, the behavior of the numerator is the same as the behavior of the leading term, and the behavior of the denominator would be the same as the behavior of the leading term as well. Now, before I move on, at this point, if you look at the limits, ignoring the lower order terms here, if you just look at the leading terms, when x goes to infinity, the numerator goes to negative infinity. When x goes to infinity, the denominator goes to positive infinity. So again, I'm ignoring these two terms. So this is an indeterminate form. So how do we find the limit? Well, we say, okay, so when x is big, only the leading terms matter, and then the limit would be what? Well, then the limit, you can see that x cubed cancels out, and as a result we get negative 6/4, which is equal to negative 3/2. So the limit in this case is negative 3/2. Similarly, if I take the limit as x goes to negative infinity, we will still get negative 3/2, because at this point, when we come to this, this equation still holds when x goes to negative infinity, and then x cubed again cancels out, so we get the same limit here. Now, when you take the limit of a function at infinity or at negative infinity, and you get a real number. So if the limit at infinity exists as a real number, then that function has a horizontal asymptote. You can see what is the meaning of this limit. It means that as x gets bigger and bigger, the value of the function is getting closer and closer to negative 3/2. So imagine that you have a horizontal line at the height negative 3/2. So the graph of this rational function then is getting closer and closer to the horizontal line at the height negative 3/2 as x goes to infinity. And you can say the same thing here. As x gets larger and larger in the negative direction, the value of the rational function here is getting closer and closer to the number negative 3/2. So this end behavior establishes the horizontal asymptote of the graph. So if you look at the graph of this, you see this is the horizontal. The blue dotted line is the horizontal asymptote. Y is equal to negative 3/2, and as x gets bigger and bigger, the graph of the function is getting closer and closer to the horizontal asymptote, and as x gets bigger and bigger in the negative direction, the graph of the function is getting closer and closer to the horizontal line as well. Now, these two, the red curves, they don't touch the horizontal asymptote here because the value of the function never achieves the value negative 3/2 here. So it's getting closer and closer to the number negative 3/2, but it doesn't quite get there. Okay, so as x approaches infinity or negative infinity, the y values approach the horizontal asymptote line, y is equal to negative 3/2 here. So the limits at infinity of rational functions, which are quotients of polynomials and horizontal asymptotes. So here we can write down a couple of general statements about this. So let's say f is a rational function where the numerator has degree m with leading coefficient am. The denominator has degree n with leading coefficient bn. Am and bn are not the same, are not zero, because if they are zero, then this wouldn't be the leading term. Now, the limit of f of x as x goes to infinity or negative infinity would be the same as the limit of the ratio of the leading terms. So when you are taking the limit of a rational function at infinity or negative infinity, you can just take the limit of the ratio of the leading terms. So here is another example. Here I have this rational function. I want to take the limit, and so I just take the limit of the ratio of the leading terms. So the leading terms are 5x to the 6 over 2x to the 5. And so these are the highest order terms. That is, these are the leading terms of the polynomials here. So now I see that after I do some cancellation, I'm getting the limit as x goes to infinity of 5/2 times x. Now notice that when x goes to infinity, it means that x gets bigger and bigger. Well, if x gets bigger and bigger, 5x over 2 is also getting bigger and bigger. So the limit would be infinity. On the other hand, if we so what we have is that this function has no horizontal asymptote because when you take the limit at infinity, it doesn't approach a real number. If it approached a real number, then we would have a horizontal asymptote. Okay, so here's an exercise where we have to find the limit of the function g at infinity and at negative infinity, and then figure out whether we have a horizontal asymptote or not. So I would like you to pause, take a moment and think about this question, and see if you can come up with an answer. And once you have thought about it, then come back to the video and match your reasoning with my solutions. Okay, so hopefully you have had a chance to think about this fraction, think about this question. So let's try to answer that. So if I'm taking the limit of g, it's a rational function, so and I am taking the limit at infinity, and therefore I can just take the limit of the ratio of the leading terms. Again, you cannot do this if you are taking the limit at a real number. If the limit point isn't infinity or negative infinity, then this equality wouldn't work. So only when you take the limit at infinity or negative infinity of a rational function, you could do this. Okay, now I see that we can cancel out we can simplify this as the limit of 2 over x, and we saw this in one of the slides that this limit is going to be 0 because we are dividing 2 by bigger and bigger denominator. So since the denominator is becoming large, the ratio would be going to 0. So we see that we have a horizontal asymptote here. The horizontal asymptote is the line y is equal to 0, and well, this is the x-axis. Now, even if you take the limit of this function at negative infinity, you would still be getting 0. So graphically speaking, when x when x gets bigger and bigger, the graph of g is getting closer and closer to the x-axis. Here is another rational function. Again, the question is the same. The question is the same. That is, does this rational function have a horizontal asymptote? What's the limit at infinity and at negative infinity? Well, in this case, again, when we take the limit of h of x at infinity or negative infinity, the limit would be the same as the limit of the ratio of the leading terms. So here the leading terms are 6x cubed and 2x cubed. X cubed cancels out, so you get the limit of 3. Well, this is a constant function then, so it doesn't change with x, so the limit would be 3. So in this case, the horizontal asymptote will be the horizontal line with equation y is equal to 3. So this is the horizontal line at height 3. So this means that the graph of h is getting closer and closer to this horizontal line as x gets bigger and bigger. Even if you take the limit at negative infinity, you will still get 3. So you get only one horizontal asymptote. Okay, so this is it. This is the end of this section on limits to infinity and at infinity. So thanks for watching, and I will see you in the next video for the next section.